So back to technology. So we're talking about basically the physics of radio communication. So one thing that's interesting is what we call the path loss. And this is the most basic fact of wireless communication, is that if you stick up an antenna and radiate it in free space, the amount of energy you receive is a function of the distance away from the transmitter. So wireless signals decay with distance from the transmitter. And in free space, the decay is proportional to the size of the wavefront. So these signals are propagating in free space. So if the signal starts at a point, let's say, and then propagates in free space, the wavefront is expanding. So we would expect that by the conservation of energy, if the energy starts out in a very small, as a very small phenomenon in space, and then expands out over this larger and larger and larger wavefront, we would expect the average energy per unit surface on that wavefront to get smaller and smaller. And generally, the size of the wavefront, basically, what I mean there is surface area. So the basic fact of radio transmission is that in three-dimensional free space, the wavefront is spherical. So think about what I mean when I mean free space. Free space means there's no floor, for example. So basically, I'm thinking in deep space, far from any surfaces, far from anything, any other physical object. The only elements in my universe are the transmitting antenna and the receiving antenna. So as I radiate, the wavefront will expand as a sphere. There's nothing to bounce off of, nothing to reflect the signal, nothing to absorb the signal. So then we have the wavefront becomes spherical. So here's what it would look like. This would be figure 1 in your notes. So here's your antenna at the center of the transmission, and surrounding it is a sphere corresponding to the wavefront. So here's your antenna. This is the spherical wavefront. And the surface area, schematically, I guess we could make it look like this. Surface area of the wavefront will tell us how quickly that signal decays. Does anybody know what the surface area is of a sphere? That's the volume. 4/3 pi r cubed is the volume. Anybody? 4 pi r squared. So surface area. Yeah, on the final exam there will be a special question just for you to calculate the volume of the sphere from first principles. Surface area of the sphere is 4 pi r squared. So more generally, the only really important factor there, the only really important feature there is that it's proportional to r squared. So for instance, if you manage to focus the beam in space so that it was on a limited angle, something like that, so that it wasn't radiating in all directions, but just down sort of a narrow angle away from the antenna, it would still decay with r squared, even though the surface area was significantly diminished. As you get further and further away from the center of the sphere, it doesn't matter what the size of that solid angle is, it will still decay proportionally to r squared. So generally, if signal decay is proportional, signal power decay, because this is power, this is not amplitude, it decays as 1 over r squared in power. Signal power decay is proportional to r to the power of d, then d is called the path loss exponent. So in free space, what's the path loss exponent? 2. So it decays proportional to r squared, so path loss exponent is 2. In practice, on the surface of Earth, surrounded by buildings, reflectors, absorbers, all kinds of crazy stuff, the path loss exponent is not generally 2. In the real world, we usually have d somewhere between 2 and 4. In extreme environments, d can go up to 6, but usually what you'll see is somewhere between 2 and 4. Yes?
In the real world, wouldn't it be less than 2? Because since these waves would get reflected, you would have more than, less loss than.
That is possible, but you would have to be in an environment where the all of the obstacles act to focus the beam rather than disperse it. That doesn't happen very often. Actually, can you think of an example of a structure that would?
Even if you had a building.
A problem?
I'm thinking like something.
Satellite dish.
Okay, yeah, but yeah. Okay.
An empty data.
I'm thinking of
Right outside home.
how about a tunnel? So if you're in a tunnel, the walls are, it's like, if it's a steel frame tunnel or something like that, the walls are conducting, so they'll basically focus your beam. That, unfortunately, that doesn't happen very often. And most generally what happens is things will tend to interfere destructively or disperse.
But even otherwise, I'm saying, wouldn't it, in general, even if I don't get any constructive interference, at least, I would at least have to leave, right? Loss.
The problem is destructive interference. So if you're close to, for instance, if you're very close to the ground, here's what happens. So there's your transmitter, and here's your receiver. You have a direct path like that, and a ground path like that. Although it is possible for those to constructively interfere, it turns out that the dominant, or the thing that dominates the performance of this is the destructive mode. So very close, in a situation like this, where the ground is considered to be a conductor, and that could be if you're if this is over the ocean or something like that. Path loss exponent in this scenario is generally considered to be somewhere around 3.